Good afternoon and welcome to Inspectioneering's latest webinar, Leveraging Data Science and Machine Learning to Improve Your Reliability and Mechanical Integrity Programs, brought to you by Pinnacle. My name is Jeremiah Wooten, and I'm really excited to have Drew Waters and Kevin Burkby with me today to talk about data science and machine learning and how different techniques are currently being leveraged to better predict corrosion rates, optimize inspections, and more accurately estimate equipment end of life. Our first speaker is Drew Waters, Director of Data Science at Pinnacle. Drew specializes in developing data-driven algorithms to enhance a variety of reliability and maintenance applications, including utilizing machine learning methods to improve and augment human decision-making. He holds doctorate in electrical and computer engineering from Rice University, and is the author of over 20 publications in the areas of signal processing, machine learning, and Bayesian statistical methods. Next, we have Kevin Burkby, partner at Pinnacle. As a senior member of Pinnacle's business development group, Kevin routinely collaborates with clients to develop custom asset integrity, reliability, and inspection programs that meet their unique needs. Before joining Pinnacle, Kevin had more than 12 years of experience designing manufacturing solutions for wood and plastic fabrication facilities. So a big thank you to Drew and Kevin for leading today's presentation, as well to Pinnacle for partnering with us to bring this webinar to the inspectioneering community. So before we begin though, a few quick housekeeping notes. First, all attendees' microphones and videos have been disabled. So if you have questions for our speakers, please submit them using the chat feature in your Zoom window at any point during the presentation. This webinar is scheduled for 1 hour, and we're going to do our best to address as many questions as we can in that time frame. But if we run out of time, rest assured your questions will be answered at a later date. Next, for those interested in continuing education credits such as API's CPD program, this webinar will qualify and a certificate of attendance will be emailed out to all attendees who watch today's webinar in its entirety. Finally, this webinar is being recorded, so if for whatever reason you have to jump off early, a replay will be made available within 1 week on inspectioneering.com. So now that that's out of the way, I'd like to go ahead and turn things over to Drew and Kevin.
Thanks so much, Jeremiah. We're excited to talk about all of this today. So to give a quick overview of what we're going to talk about, we're talking about machine learning and data science. We're going to talk about what that actually means, just to demystify some of those terms, because they get thrown around a lot in our industry. What we're going to do after that is walk through a couple of ways that how we at Pinnacle have leveraged data science and machine learning for reliability problems. We're going to talk about data quality issues and ways that you can potentially clean up noisy or erroneous data. We're going to talk about predicting corrosion rates using data. We're going to then switch gears and talk a little bit about predicting equipment end of life using inspection data. We're going to talk about ways to kind of prioritize inspection plans and to kind of optimize inspection plans using data. And then we're going to end talking a little bit about how we can leverage text data. Text data presents a number of challenges and fun opportunities for us. So we'll hit all of that for us. So with that having been said, let's talk about what data science and machine learning are. So data science in a nutshell is the science of trying to extract information from data. We know that right now in our industry, we're sitting on a treasure trove of data. We have so much data at our fingertips. Where the problem lies for us is that it's very, very hard for individual humans to get any real insight out of such voluminous data. We simply don't have the computational power or the human bandwidth to be able to manage that. Data science comes in and lets us do things in a more automated and efficient way, and potentially allow us to leverage some of that data more efficiently. Machine learning, on the other hand, is related to data science, though it's separate. Machine learning is a branch of computer science that is meant to train algorithms to kind of learn from data and make inferences on its own. Data science kind of lives at a nice intersection between a couple of different disciplines. Data science is usually seen as kind of the intersection of applied math, statistics, computer science, engineering, and also business to an extent. But when you blend all of these things together, the data science and the machine learning has some pretty amazing potential to revolutionize the way that we do things in our industry. So we're excited to talk about that with all of you today. As I mentioned before, big data is kind of a double-edged sword for us. On one hand, we have a tremendous amount of access to data. We save everything that we do electronically. We have gigabytes and terabytes upon terabytes of data at our disposal. The downside of that is what we call in our industry the data deluge. You're flooded with data. There's way too much data for any human to adequately analyze. And so on one hand, we've got all this data that we'd love to be able to do things with, but we have less and less capacity to do anything meaningful with it. One of the other downsides of the data that we've got right now is that our data is often plagued with quality issues. We're very familiar with this in our industry, and we'll give more concrete examples of that as we go through this presentation. But bad data on one hand can lead to really bad inference. If you don't have good data, you can make very bad decisions on bad data. But it's also one thing that we'll discuss momentarily is ways that machines can potentially clean up that data, help us kind of correct some of those problems before we get too deep into things. So with that, let's talk about that a little bit. Let's talk about data quality issues.
Yeah, and just to preface this a little bit, I think if I could see everyone's hands that had called in and I said, raise your hand if you think you've got data quality issues. Thickness data is probably the biggest culprit in our business, at least the one that we hear the most about. But huge amount of people say, man, I know that the data we have isn't good. I think there's where it gets fuzzy is which data isn't good, which can I trust? How can I use that data? And there's a lot of skepticism around, man, let's leverage our thickness data to make other decisions in the plant. And it's like, man, if it's not 100%, I don't know that I want to go use that data. So this is a very pertinent topic for something that we run into all the time. So, and these are real examples of how we've applied these techniques to kind of cut out some of the noise.
Okay, very good. So yeah, Kevin mentioned inspection data, and we'll give an example on that right now. So what I've done here is I'm showing 1 CML worth of inspection data. We've got data from about 2002 to about 2019. I've got a couple of inspection points for this CML. We're looking at thickness readings. So I've got the measurement value on my y-axis. I've got time on my x-axis. And I've got a couple of points on here, and I've colored them a little differently. So most of my points are red. With the red points, you can see kind of typical thinning behavior. I don't necessarily have every point getting thinner and thinner over time, but there is an overall trend where we're seeing this, the thickness of this material is going down over time. It's what we expect. Now, one of the weird things that's going on with this CML is shown in the blue point up at the top. So on this blue point that we have, we've got, it's an outlier data point. There's nothing that makes sense of this data point. Like CMLs don't grow over time. The weird outlier high measurement value that we've got there at blue is more likely due to erroneous data or erroneous inspection techniques than anything that's actually physically going on in our system. Now, why do we care about this? Well, if I'm looking at things like corrosion rates, or I want to predict equipment end of life, bad data can very much skew the way that I'm going to interpret the reality of my asset. If I had a really, really high measurement value towards the end of this time series, I might grotesquely underestimate the amount of thinning that's going on. That's not something I want to do. I want to have a good, accurate estimate. And so one of the things that we have to do when we look at this data is we've got to quarantine some of our inspection measurements. And we have to ask ourselves the question of, do I trust this measurement or do I not trust this measurement? Now, one thing that is, I guess, looking at this one example right here, I would imagine most people on the call could probably figure out, hey, that blue point is bad. Something's wrong with it. What's harder for us to do is to do this efficiently over, say, thousands or tens of thousands of CMLs.
Hundreds of thousands of
them, which is our
typical.
Yeah. So while a human can handle this for one, trying to do this over 100,000 is a bridge too far. We're not going to be able to do that. But this is where the machine can come in. Machine learning data science techniques can take a look at all of this data longitudinally across hundreds of thousands of CMLs and be able to identify the points that it thinks are questionable. In the graph that we're showing, the red trend line that we've drawn on here, that's capturing thinning behavior really well. This is something that we'd expect to see happen. That red trend line, however, is completely at odds with the blue data point that we've got. What this does is it enables a machine to go ahead and start quarantining data points that it thinks are suspect. Now, on one end, we could automatically remove those or discount them from any further analysis. If we're scared of the machine and we're not sure if the machine's always going to make the right decision, we can also quarantine these points and we can then present them to a subject matter expert for validation. We can keep the human in the loop, but still give the human the best tools at their disposal to make the best decisions that they possibly can. Here's another great example of poor data quality. So here what I'm doing is I am showing multiple CMLs worth of data. We've got three CMLs here. We're looking at time again on the x-axis. We're looking at thickness on the y-axis. And one thing that we notice if we look at the first 3 data points is that they're very, very low. And then after a certain point in time in say 2014, where I've got a green vertical line, all of a sudden my thickness gets much, much larger. What's going on here? Well, what's happened here is that there's a repair that's happened on this particular piece of equipment that hasn't been disclosed. Nobody wrote down in the data set that the repair had happened. So again, if I were to try to analyze what's going on with thickness over time, this looks like the CML is growing. It looks like we're getting thicker over time. Doesn't make sense. I don't want that. Again, for a human to look at this, most humans could figure out, hey, something happened. There's a step change that happened with our data.
Sure.
But to do this automatically over, again, hundreds of thousands of assets and components is difficult. The machine makes this easy for us. So in this case, the green line that we've estimated here, this was done by a machine going through data that a customer had given to us. Machine was able to flag this. We were able to take this back to the customer and say, hey, we think something happened on or around this time. Customer was able to confirm that in this case. And so we were good and we could continue on with our analysis. But if we hadn't done this step right here, if we hadn't tried to resolve that data quality issue, we would have been in trouble for later analysis. So this kind of thing is important for us.
Yeah, it's just a couple good examples of how you're going to integrate, at least at the front end of a project until you're confident in what the machine is telling you, that get that external validation, whether it be SMEs or follow-up inspection readings or somebody go out in the field and validate what's going on. But looking through systems, because I promise nobody's ever accidentally forgot to note that something got replaced in the field, right?
No, for sure. And that's, I guess, one thing that we've always advocated for. I mean, I'm a data scientist by training. I love data science. I love machine learning. I understand the limitations of data science and machine learning. And so where we have always tried to position ourselves in the industry is that we are a data-driven company. We want to do data-driven reliability, and we want to use cool data science, cool machine learning, cool computer science techniques. But we understand that we can't divorce ourselves from subject matter expertise. If you're doing that, it's a recipe for disaster. Your machine can go off the rails and do some very interesting things that you don't want.
Well, I think it's a good note to set expectations, even throughout the rest of the presentation, on what the limitations of machine learning are, and the notion that it will operate unsupervised and generate perfect results is a misnomer.
No, completely agree. All right.
So whether you have an RBI program or whether you're just trying to project the rest of the life for an asset, people are using corrosion rates and trying to establish corrosion rates all over our industry. And I'd say probably one of the examples when it's difficult is when you don't have good data to depend on. And so usually what happens is through the implementation of an RBI program, you gather a bunch of people in a room, you review process conditions and metallurgies, and man, if you have some data either from similar service or on those assets, trying to leverage that. And then it typically comes down to whether it's an SME or corrosion engineer saying, and kind of based on conditions, based on models, based on tables in 571, whatever that might be, I'm going to assign a modeled rate to this CML or to this asset. I'm going to year, 5 mils per year, 30 mils per year. You need to change the material. The interesting thing is, I don't think, and I've sat through several of these, call them a DMR, call them a corrosion model validation meeting. I don't know that I've ever left one that had a mils per year expectation less than 3. Okay, so maybe somebody says it's 2 or something along those lines, but very seldom is it less than 3 mils per year as a guess. And man, we're pretty sure that's pretty conservative, at least across the board.
Yeah.
So how can we use data to better predict what corrosion rates will be on assets. And we've got some good examples here.
All right. So let's talk a little bit about theoretical versus real world corrosion. So plot over on the left, what I'm doing here is, this is from the API spec, but it's hydrochloric acid corrosion. We've got pH on our x-axis, we've got corrosion rate on the y-axis, we've got curves for different levels of temperature. So we kind of see the things that we sort of expect here. As pH gets lower, I get more acidic, I'm gonna have higher corrosion. As my temperature increases, I'm going to have higher corrosion. This plot on the left is a theoretical plot. This is lab conditions. This is sort of what we expect to see happen given what we understand about this process. Now, what I've done over on the right is I've shown for just one single point on the graph on the left, for one pH, one temperature, let's say that we have a CML that is operating at those conditions. I would expect to see thickness decay with some profile like what I'm showing over on the right. The black line is my expectation. The gray shaded region maybe captures some of the uncertainty that I have. My pH is a little off. My temperature is a little bit off. It varies a little bit over time.
Think of it like a hurricane projection cone,
perfect.
right? Cone of uncertainty.
Yeah. Perfect, yeah. What I'm expecting to see is that when I go out and I do inspections, my data points should probably live within that hurricane tracker if things are kind of matching theory. Well, here's example data from what we've got on the next slide. So this is real data that we've plotted for a single CML under these conditions. And most of the data does not live within that cone whatsoever. What I'm taking away from this is that we have a theoretical expectation of what corrosion should look like. And it's not horribly wrong, but it's also, it fails to take into account some of the real world aspects that happen at your actual facility. We know at your facility, there's different maintenance teams, there's different environmental conditions, there's all kinds of other things that work together to influence that corrosion rate. And if all we're doing is we're looking at theoretical rates, we're gonna miss all of that extra stuff. And we can do better, we can be more nuanced about that. So one thing that we did a couple of months ago was put together a study where we were looking at corrosion rates within reformer units. And so we'll see some examples of that in just a second. There we go. Okay, perfect. Okay, here we go. So we would like to be able to estimate corrosion rates from data. What we're going to talk about is a study that we did that was limited towards reformer assets. We've done this for other units. We've done this for crude units and hydrocrackers. We're just going to limit this to reformer. But the data that we're looking at consisted of about 20 facilities worth of data, about 36 units, roughly 10,000 assets. When we did a back of the envelope calculation on this, turns out to be about 10% of the US reformer market, maybe about 2% of the worldwide reformer market. So it's not everything in terms of data, but it's still a significant data set that we're working with here. But what we wanted to do was develop a data-driven method for estimating corrosion rates, and also be able to compare that model, that machine learning data science model, some of the industry standard approaches and with human subject matter experts to see how well things came out. Some of the data that we used in this, so with the data set that we're working with, we have our inspection date, we have the measured thickness. That lets me compute a corrosion rate. That's the real corrosion rate that's experienced in the system. And we're using that as kind of the output that we want to predict. Some of the things that I've got on the input, I've got location information. So I know which operator I'm looking at. I know which site I'm looking at within that operator's ecosystem. I've got asset conditions. I've got temperature, pressure, metallurgy, whether the asset was insulated, whether PWHD was applied. I've got stream information. So I've got things like the H2S content, the water mole percentage, the ammonia content, all of those things that we're used to dealing with.
And presumably the inspection data is insufficient. The reason you're trying to predict corrosion rates is because I don't have good data.
I don't have
on these things to say this is the corrosion rate. Exactly. Hence I'm predicting them.
Yeah, so, because when we look at the inspection data, sometimes I get lucky and I see something that's maybe kind of linear and going down over time, which is what you'd expect. Sometimes it's more of a shotgun blast. It might be all over the place.
Yeah, or sometimes there's none.
Yeah, and sometimes there's none, definitely. So we're trying to do the best job that we can here and then kind of correlate with what data we do have to see if this works well or not. Yeah. So we have our model. What we're using is a technique that's called supervised machine learning. Let me demystify that for a second. When we say it's supervised machine learning, that means that I'm training a machine learning algorithm to make predictions, but I'm telling it what the right answers are. So think of a giant Excel table. Every row in my Excel table is a different CML that I've got access to. All the columns are all the things like the temperature, the pressure, the metallurgy, the H2S content. The corrosion rate is in there too. That's my output that I'm learning on. What the machine is going to do is it's going to crunch on every single one of those rows in the Excel workbook, and it's going to organically learn what drives corrosion and what doesn't drive corrosion. We know, for example, that at higher temperatures, I expect to see higher corrosion. We haven't told that to the machine. The machine is just going to learn that organically as it starts to filter through data. But when everything is done, if our algorithm is doing a good job, our model is going to be able to output an estimated corrosion rate for a new CML that it's never seen before, with maybe different operating conditions, different metallurgies, that kind of stuff. It's also going to give us an idea of what things matter and what things don't matter when it's making its prediction. Now, why is that important? That's important for when we validate this with the subject matter expert. If our model says that certain things matter that really do matter in the mind of an SME, that's a good check on our model. So that's another nice thing that we get out of this. So here's an example of what a corrosion rate estimate might look like. So let's say I've trained my model. My model kind of has an idea of how temperature, pressure, all these things affect corrosion. What I might be able to do afterwards is say, okay, I'm going to give you a new CML. This CML has this side information. So these temperatures, pressures. What I've done over here on the right is I'm showing a plot that the model both gives us a rate that it thinks is going to happen, but it gives us uncertainty around there. As far as our model is concerned, anything that's living kind of between 3 and 8 mils per year for this given CML is something reasonable. It's about 80% confident that it can have something kind of in that range. The actual corrosion rate for this CML is the blue dash line, the vertical blue dash line that you're seeing. It's pretty close to the peak of what our model's predicting. Like, we're not very far off from what we expect to see happen. But what was nice is that when we looked at this longitudinally for a wide variety of CML data, most of our predictions fell within that interval. It's a good check on our model. It says that we're doing okay here. But I guess the thing that I'll emphasize here is that the model is really good about telling you what it knows, but it's also really good about telling you what it doesn't know. If it has very high uncertainty, use that in their decision-making process. Tell you that it has. So we did this model. Begs the question, is this model any good? And if it is, we did a test where we're just testing how the model does on data that we already have access to. Second thing we're going to do is put this head to head with a human. So let's talk about what we did here. So the cross-validation test, this is where, like, I can't give the machine something that it's already seen and ask it to make a prediction on it. That would be considered cheating. The machine's going to do really well on it because it already knows the answer. Instead, what we're going to do is I divide up my data into little segments. We call those little blocks segments of data. What I'm going to do is I'm going to train my model. The model's going to learn how corrosion works again on some subset of the data. In this case, it's going to see about 80% of the data that's available. 20% of that data is going to be ignored by the model. Once the model's been trained, it's going to go make predictions on that test set of data that it's never seen before. But because we have the answers for that data, we can evaluate how well the model does on things. We can repeat that for a lot of different cuts of the data. When we do this, our overall average error comes out to be about 2.2 mils per year across all the data that we had access to from this reformer study. So down there. Good result right there. We're feeling pretty nice about 2 mils per year. Second thing that we did is we compared this with a human subject matter expert. So what we did here is we held out 11 assets from our data set. We retrained the machine learning model. So the model sees everything that's not contained in those 11 assets because, again, we don't want to cheat. What we also did is we gave all of the data to a human subject matter expert, an engineer who had 10 plus years of experience working on these kinds of data sets. And we had them come up with their own predictions. Okay, what do you think the corrosion rate is going to be on this? Given all the experience that you've gained over the course of your career, all of the data that we've provided to you, what do you think is going to happen? Now we can compare the two and see what happens. So here's the results on that. We looked at 11 different components here. Green indicates who the winner is. So of the 11 components that we looked at, the machine performed better than the human on 8 of the 11 assets. That's a really good indicator that the machine's doing a good job. What we can also do is we can look at just how far off are both the human and the machine when making these predictions. And what we get are the results that are on the bottom of the table here. Overall mean absolute error for the machine is about 3.1 mils per year. It's a little higher than what we saw with our internal testing. These were tougher components that we're looking at. Human was off by about 5 mils per year. So while the model is maybe off by 73% on average, humans off by 184%. So another nice win for the machine.
Yeah, substantial difference. And it's you would expect with a human for as the data set grows or the assets that you're looking at grows, your potential for error increases just because the focus or whatever that might be, or the time in order to do it increases substantially. Not so with a machine. So
yeah, very good.
Yeah.
All right.
So why do we want corrosion rates? And as an example, a lot of difficulty in determining what's the end of the life for my asset. Now, we'll talk a little bit about thinning specifically as something progresses toward its end of life, but there's similar challenges that can be solved on all kinds of different assets, fixed and non-fixed, across the industry using data science and trying to predict as you progress towards some terminal date, where am I on that plot or on that path? So this is interesting stuff.
So we are going to limit everything to thinning right now, just to keep things simple. Like Kevin said, you can apply this to a wide variety of assets and degradation patterns. We're just going to talk about thinning here. So what we're going to do is introduce a concept that we call the lifetime variability curve. Going back to what Kevin said earlier about hurricane trackers, you can think of the plot over on the right as being a hurricane tracker. I've got some data points. Those are my blue points that I've got with the error bar tails. The blue shaded region is describing what we think the actual wall thickness at this location could be at any given point in time. And ultimately, what we're interested in is figuring out when we're going to cross the big, scary horizontal blue dashed line at the bottom. That's our critical value. For all intents and purposes, when the thickness of our component gets to that level, we have failed. We would like to be able to detect failure before it happens and then go out and do something about it and mitigate those problems.
Yeah, to use industry jargon, that's what you have determined your T-min to be, is that blue dotted line across there. Whether it's a flag, nominalized corrosion allowance, whether you've done full studies in order to determine your minimum thickness, that's what's being represented by that blue line.
Perfect. So how does this model work? Well, it takes in two pieces of information. One of them is the data and our trust in the data. For this plot, I've got 5 data points. I maybe have a certain amount of error that I tolerate with every measurement. We know you never get the right measurement. It's always something kind of in the ballpark of what was actually returned by your equipment. But then what's kind of special about the method we developed is that it also takes into account prior information that could be given by, say, a subject matter expert. So going back to the DMR conversation, group of engineers sit in the room, they decide the corrosion rate should be about 5 mils per year. That's the starting point for our model. We can't just trust the data itself because we know data has quality issues. And especially when we're data poor, I may only have 2 or 3 data points.
Yeah.
I can't trust the data alone. That would be a bad decision for me. But if I'm incorporating that subject matter expert information, I now have 2 sources of truth that are kind of can potentially be in conflict or can potentially agree with each other. That ultimately gives us a better prediction that we're going to feel more comfortable with. What I can do after I fit this model is I can come up with a probability of failure curve. That's the subplot on the bottom with the green line. What this is saying is that the POF is the probability that you will have failed on or before some particular point in time. So what the POF curve here is saying is that prior to, say, maybe 2023, 2024, there's no probability of failure. Everything's fine. Yep. You don't need to be worried about anything. Conversely, after about 2040, there's absolutely no way that this asset is going to be okay after 2040 unless something changes with your data. Based on what we've seen, we expect you to fail sometime within those 2 bounds right there. And the probability that you failed at any point in time is given by that curve. So what we can do with this now is we can talk about what happens as we add more and more data to this. So let's say we're starting out our analysis. I have a single data point. This case, it's just probably the nominal thickness. This is what the factory has reported. We haven't even done an inspection yet, but we have a single data point that we think represents reality at installation date. Our model comes in with 1 data point. It's going to basically rely entirely on the subject matter expert rate. And the blue cone that we see is the projection of what we think that SME rate is telling us. SME might say 5 mils per year plus or minus 1 mil per year. That's the cone that we've got. So we've got bounds on when things are supposed to fail. We have a probability of failure curve. Now let's go to the second plot. I've added 2 more data points. I've added more data, but if you notice, my uncertainty grew.
Increased substantially, yes.
Yeah. So what's going on here? Well, what's happened is that if you look at my data, my data is all in a nice straight line. And if you were to draw a straight line through those data points, it's predicting a failure rate way out in the future. I mean, kind of past 2050, 2060. What the data is telling us right now is that corrosion is not as severe as what the subject matter expert indicated. It seems much less severe. And so now I've got a bit of a conflict. On one hand, my SME is predicting earlier failure, say maybe around 2025, 2030. The data is predicting something further out, 2050, 2060. What are we going to do? Well, with 3 data points, I don't have an overwhelming amount of data trust. The model is kind of reacting to both of those sources of input, and it's giving me a very, very wide range of potential failure dates. Totally possible that my data is erroneous. I might still fail in 2025, 2030, but if my data is telling the story that it is, and it's consistent with that, I could live a lot longer. Let's move over to the third plot. I add 2 more data points. I have 5 data points now. Right now, my confidence has increased significantly. I've collapsed really close to around that 2025 to 2035 range. Because what's happened with my data is that the new data points are now in very strong agreement with my subject matter expert. It looks like corrosion's accelerated a little bit if I just look at the data. But now taking all of that into account, the model's really reasonably certain about what's going on. Corrosion is more or less what the SME decided. We have an idea of when things are going to fail. But we were able to take both of those sources of data together to arrive at that and thereby get a much more robust estimate than what we would get if I were just listening to the SME or if I were just listening to the data.
As you increase data points, you decrease the weighting of the SME as you go through there.
Yeah, we do. So, and this is the very natural, like kind of math thing. It's not like a human coded rule that we have in here. This is going back to fundamental statistics of if you've got data and you have a certain amount of trust in that data, what is the right weighting between subject matter expert and data? And all of those things come into play. If I have looser confidence on all of my individual data points, I'm going to require more data to get that data confidence up. Right. But if I say, hey, there's absolutely no error in this data is absolutely perfect.
Yeah, you're laying several of the techniques we've talked about with regard to cleansing data and making sure you don't have erroneous readings, and maybe even taking some of your predicted rates from machine learning and then putting SMEs in there. Now, when all those things line up, you're going to get a pretty tight cone with regard to what's going on.
Yeah, exactly. Awesome. Yeah. All right.
So this one's interesting, and we were pretty careful not to use the term CML optimization on this slide. However, this is CML optimization, right? So what can you do as you start to develop and leveraging those LVCs that we've created? And you want to start deciding, and I've got all these spots where I'm taking data, which ones are really important to me? Which ones really tell me something? And there's CML optimization tends to be a buzzword that kind of gets thrown around, and it can mean a lot of different things. But let's, for the sake of argument, let's stay in our general thinning lane that we were using on the last slide, or in the thinning lane, and talk about how can we leverage this to prioritize the places where I need to go take thickness readings.
Okay. All right, so before we jump into the specifics of the method that we're using here, let's just talk about a really neat observation that's consequential for us.
Yes, pretty fundamental in this whole thing.
This one's huge. So remember, our LVC model kind of estimates our probability of failure over time for every CML that we've got in our population. If I want to talk about risk instead of probability of failure, risk is just probability times consequence. So my LVC model can also give me an idea of how risk is evolving over time. Now, let's say that I take a bunch of data within a facility, and I want to say, how is risk spread throughout the entire facility at any given point in time? Well, when we carried out this study on actual real data, and we've done this multiple times for multiple different customers, and we see the same behavior every single time. It's something that sounds a lot like the Pareto principle. And we're showing it in the graph over on the right side of the slide. The amount of the CML population that drives your risk is extremely concentrated. What I mean by that is that it's generally about 20% of your CMLs that are driving maybe 80 to 90% of the overall risk that you've got. This is really cool. It makes sense. Like, I think everybody probably is on the same page with
Pareto principle works for a reason, right?
Yeah, sure, it does. But this is like, and the graph that we have here, this is with real data. This is not us just saying, hey, Pareto's principle is real, let's use it. This is like actually measured and validated.
I mean, to air out a little bit of internal dirty laundry, like the first time this was presented to some of us, we're like, yeah, okay, cool, but you can't just assume Pareto's right. And they're like, no, this is real, actual data that just turns out to support it very, very closely. So that's important to note. This was not just kind of a, oh yeah, man, it looks like it's about that. No, the data bears this out. As we look at more and more facilities, it's just supporting this even more so far.
But because we've got this concentration, and again, this is validated risk concentration, you can do smart things. You can focus your attention on the things that matter, and you can focus your attention away from the things that don't matter, at least right now, the things that don't matter right now. If our risk was spread uniformly across all the CMLs in your facility, you'd be dead. You can't do anything. You'd have to go inspect everything to be able to cover your bases. What we're saying is that you can do something a bit smarter, and that's what we're going to get into now. So there we go. So let's go from the LVCs to inspection optimization. So again, my LVC curve gives me an idea of risk over time. If I'm looking at multiple CMLs, say on a piping circuit or on one asset, I can start asking questions of which CML is likely to drive failure on my asset or my component. What I might have is something over on the right where I've got failure density curves for maybe two different CMLs. I've got pink CML and I've got blue CML. When I look at this, I'm saying, okay, pink CML is more than likely the one that's going to drive failure. It looks like it's going to fail maybe a good 30, 60 days prior to the blue one, but there's overlap between the two. There's a chance blue could fail first. The game that we're trying to play with our take on CML optimization or inspection prioritization is identifying the CMLs that are likely to drive failure or that are strongly contributing to overall risk, and then focusing our attention on those and making sure that we're covering our bases where it should be done. So here, if I'm looking at another way of looking at this is again risk over time. Let's say I've got 4 CMLs here. I'm looking at risk over time. What I might be able to do is say, hey, as a facility, I may have a certain tolerance for risk. And I'm going to show that with the black dotted line that's over at about $100,000. What I might say is, hey, I'm looking forward to a next turnaround cycle. When my turnaround comes around, I've got a carte blanche to go do inspections. I can repair equipment. I don't have to worry about downtime in the same way that I do when my facility is operational. What do I need to do now that I've got my chance to go inspect and repair? Well, what's happening here is that the LVC model has produced these risk curves, and we're looking for the CMLs that are going to cross our risk threshold on or before the time that we care about. Time that we care about is around 2030. It's the dashed vertical blue line. What we're seeing on this graph is that at this point in time, I care about 3 CMLs. I care about the blue CML, I care about the red CML, and I care about the purple CML. Those have all breached my risk threshold or will have breached my risk threshold at the time that I care about. But the green CML, CML number 3, is below my risk threshold. I don't have to care about that CML right now. I'm going to have to care about him down the road.
Yes.
He's peaking up.
It's important to note that it doesn't mean it's gone away.
Yeah. We're not eliminating CMLs here. We're just talking about what you care about right now and what requires your attention right now. Things that don't require your attention right now will require your attention later. But we can be smart about things, and that's a good place for us to be. Another example coming up here. Okay, so this is, there's a lot going on in this example. We'll cover this briefly, but here I'm looking at a piping circuit. It's a dead leg. It's got 38 CMLs in total. We ran our LVC model on all of the data that was presented to us. We were able to project what thickness would look like at a future date in 2025, which was the next turnaround for this facility. What we ended up finding was that to be 95% confident that I've identified the CML that is going to drive failure on this piece of equipment, I only needed about 7 CMLs, and those are the ones that I'm showing over on the right-hand side, and I'm summing up their cumulative contribution to failure. I'm 95% sure that the one that's going to end my life on this piping circuit has been identified in this set. It's possible one of the other ones would do it, but it's diminishing returns for me to keep including them. I'm still going to have to pay to inspect them. I'm going to have to spend time doing it, but they're not doing a lot to reduce my risk at this point. So I can be smart and I can allocate my resources in a smart way. All right. Here is a fun case study that we did. This was with a refinery customer a year or so ago. We did a very simplified study. We're looking at 3 units, consisted of 6 piping systems with about 400 CMLs in it. These assets traditionally have had very, very high corrosion rates due to sulfidation and erosion. So very, very nasty stuff that this facility is working with, and lots of problems there. If the facility were to go inspect every CML in their facility for these assets here, it's going to cost about $738,000. They're going to have to inspect all 382 CMLs. And once everything is done, there's a certain amount of risk that they're going to have after doing all of this inspection work. It's about $97,000. If we utilize our approach for prioritizing things that they inspect, they're able to cut that total cost in half. They're able to do half of the CMLs, but the risk that they have, and we're being kind of generous with the risk here, only increased about $2,000. Very, very small amount here. And again, I say we're being generous with risk. If you think about it, this is actually more risk optimal. Instead of trying to spread your resources across everything and maybe doing a substandard job on that inspection, if you can focus on the things that matter, you are potentially reducing your risk below what you would have if you were to inspect everything, because you're doing the smart thing, you're doing the right thing, you're making better decisions overall.
Yeah, I mean, the question is not to get your risk as low as possible. The question is, at what's the amount of risk I'm willing to accept in order to optimize for cost and risk? Huge win there.
Okay.
So 2 examples coming out of this, textual data for reliability, open text fields, people typing things in instead of selecting from a drop-down menu, or these aren't data values. And there's a couple examples of projects here that I'm very familiar with. Andrew and I worked on them together. So, but there's a lot of data that gets created across our plants. And some of them are numbers, but a vast amount of it is language, is words that get typed in. Maybe right, maybe wrong, but I think people assume that data isn't usable. Man, I've got to have numbers. They got to be trendable. They've got to be something that I can compare against another thing. Not so fast. We'll show you how that stuff can be used in some very cool ways across 2 specific examples.
Yeah. So again, text data is hard. We're all very comfortable with numbers. We're used to doing regression models. We're used to like adding and subtracting things. Like this is all natural stuff for us engineer types. Text makes things more difficult because words are hard. Some of the things that we have to deal with, I mean, data quality issues still apply with words. We have to deal with things like misspellings. I have to do with word variants, like things like run, running, or ran. It's the same word, but it looks different to a computer because they're typed differently. The 2 examples we're going to talk about that are very much in this avenue of language processing. First, our topic modeling for an incident logs data system. We're also going to talk about positive material identification, and I think we'll have some cool insights on both of these. So let's tee up the incident log data problem. The problem here is that we had a customer that had a reporting system for any incident that was seen in the facility, and for any of their facilities. It was across 15 sites. Problems could range from loss of primary containment, so a leak actually occurred somewhere, to an H2S alarm went off, or security saw a suspicious vehicle in the parking lot. I mean, it just runs the gamut on all the things that you could think of that show up in this database. The different stakeholders within the organization cared about different subsections of those incidents, but there wasn't a nice way to code them. It was just a text dump. And so every person was getting a huge dump of all the incidences. It was difficult to figure out what was relevant, what wasn't. So we tried some data science techniques to see what we could do here.
And important note, there's no other information.
Yeah.
It's an open text field and a date.
Yeah.
Maybe a time, but like, you didn't know where it occurred. An area, just an open field.
Exactly.
So trying to parse that out.
Made it hard. One of the initial attempts of this project was to just try to hand code. If I see these words, call it this. If I see these words, call it this. Handling textual data for the reasons that we mentioned already. Words are hard, words have variance, people misspell things. There's all kinds of things that will foul up a kind of a rules-based system like that. So what we tried to do instead was do automatic topic modeling. We're going to give this information to a machine. We're going to let the machine use all of its processing power to make sense of everything and categorize things in the smartest way that it can. So the technique that we used on this, I won't dwell on this too much. It's called latent Dirichlet allocation. If you ever want to Google this is some fun stuff here. Best example I can give of LDA is talking about newspaper articles. So say you're reading the newspaper or you're online because it's not the 90s anymore. News stories have different topics associated with them. I may have a newspaper article about politics, and I'll see words in that article that are very political. I'll see things like Senate or Supreme Court or president or congressman or something like that. I have articles that talk about sports. I'm going to see things like NBA, NFL, football, golf, Tiger Woods, all that kind of stuff. Those words can occur outside of in a different context, but they're very concentrated, right? Like the topic that you're reading about tells you what words you expect to see and vice versa. What topic modeling does in the hands of a machine is the machine is simply looking at what words occur together with some kind of frequency. And if it can do that, it can learn what different topics are and what are the words associated with those topics. If it's able to learn a topic representation, now what it can do is it can go and categorize every news article as belonging to politics or sports or community affairs or any other topic that you want. Now, in our case, we're talking about an incident data log, and we're talking about words that show up in the incident log and like what kind of incident we're talking about. The animation that we're showing here, every circle on here is a different topic. The topic that we're looking at right now is a topic about pumps and leaks primarily. So anything that kind of talks about pumps, leaks, that kind of stuff shows up here. Here we've got a topic more about valves, things like that. This one is more about personal alarms going off. So H2S alarms, levels being tripped. This one is very medical focused. It's about first aid station, that kind of stuff. But this was all something that the computer learned here. Computer has no idea what an H2S alarm is. It has no idea what a valve is. It doesn't understand what a pump is. It doesn't understand what first aid is. All it's doing is using math to try to understand the stuff that we've given it. And it's come up with something very reasonable. And this was a very good categorization of the log data that we ran into.
On this project, the customer had created a set of buckets. Like, hey, I want to classify these things in these buckets. And so the original, as you said, more brittle approach was, man, read these things and figure out which one of these buckets it goes into. Now, when a human does that, the initial inclination is you put it in a bucket and now it's gone. Well, you have leaks and you have valves as two different categories. I could have a leak and a valve, and that needs to be in two different buckets. But what was interesting is when you let the machine determine its own categories and machine, man, the buckets that the customer created and the buckets that the machine created, man, they lined up pretty well. And it optimized some of them and said, yeah, you don't need those categories. Those weren't as important. But the other thing is, hey, here's some new categories that you hadn't thought of. So letting loose of the technology to let it go do what it could brought some really interesting insights.
Very good. Oh, here's a fun little result that happened too. So looking at we didn't go into this project expecting this. This was something kind of fun that happened with it. What we're doing here, every graph here is a site within this customer's ecosystem. What we're doing here is we're looking at the frequency of incidents over time. Some of them you can see are somewhat constant. Some have trends where they dip down, maybe peak back up, or they go the other way. It was kind of fun. It gave some insights into the reporting culture at every site within their ecosystem.
So one of the things that doesn't show up in the data here is across 15 refineries, there was 3 of them that didn't use the system, right? That's pretty clear. What's interesting is the quantity of reporting, and you can see this better when this gets sent out with the values, is not necessarily indicative of the size of the facility. So you would presume that a 100,000 barrel a day facility is going to have less incidents than a 400,000 barrel a day facility. But what's interesting is you saw this particular refiner had several of them that were in that kind of 250 to 300 range. I mean, those numbers varied wildly. And what that taught the operator, the owner, was, man, I have either very different practices happening in these places that is minimizing incidents. And so I'm able to trend information across sites, or man, maybe I have a reporting culture that's different in these places where, man, things aren't necessarily making their way into this system, or it's not being utilized the same way across different places. So we did not dive too deep into this, but this was a cool thing that came out of the being able to put all of these data sets next to each other and look at it visually. It's kind of it was an unintended insight in doing this.
We'll switch gears. How much time do we have right now?
10 minutes, 11 minutes.
Okay, we're good. So we're going to switch gears, talk about positive material.
Certainly at the begining of it. So again, different refiner, multiple facilities in the same range, 13, 14 different facilities, somewhere in there, have a material intake form that gets filled out when they order new components. And based on the conditions of whatever that component or that supply is that they're ordering, there's a decision that gets made. Does this need to have a PMI inspection done on it? Do I need to verify that when I ordered something that was stainless, that it came in and it was stainless or Inconel or Monel. As a lot of people know, making sure you have the right material installed in the right service is critical in some of the units we had. This was driven by kind of a focus on HF alkeys, where it's even more critical. So low residual elements versus high, and dissimilar metal welds in certain places, or just the wrong material in the wrong service can make a really big difference in the reliability and in the safety of your facility. So this was critical, and they had traced some potential issues. I wouldn't say issues, some potential issues back to, man, are we checking that box right, and are we doing the follow-up inspections appropriately across a massive data set? Is actually, this has 300,000 entries. It was closer to 500,000 entries, and the time it would take an expert, whatever that expert is deemed to be, to go through 500,000 entries is massive. Not to speak of the fact I'm tying up a very important person to read through 500,000 records across 13, 14 refineries to go back and look for these. It probably doesn't get done well, or it probably just doesn't get done quickly. And so they came to us saying, is there ways that you can leverage cool data stuff, I think is kind of how it was put to us, to figure out a better way to give us some focus on this.
And the answer is yes, we can. So we did that. So again, the wrong approach on this is to do something brute force. If I were to give it a list of terms, okay, if you see Monel, it's PMI, and if it's carbon steel, it's not PMI. I can do that. That's going to give me a certain amount of lift, but it's brittle. And again, it's only as good as the word list that we come up with. If we miss something, if we don't include all the proper ways that you can spell 347SS, we're going to miss things, and we don't want that. Also, context is kind of a big deal in this problem. So the word steel can be misleading. So carbon steel and stainless steel are very, very different. They have very different PMI rules associated with them. So we have to be careful with kind of that simple brute force approach. Machine can do better, and it can do better faster. So we stick to the machine on this. Machine was given the data along with the PMI labels that had been previously assigned to all the entries in the data set. The machine could then infer somewhat naturally, what are the PMI indicating words? What are the not PMI indicating words? What makes me think PMI? What makes me think not PMI? The machine can deal with a lot of those pre-processing issues better than a human can. The things like the spelling, the compound terms, all of that kind of stuff. But when everything is done, we've got an approach that's much more robust than the brute force approach, and ended up doing very, very well with the results that we had. So I'm not advancing. Has my battery died? I don't think it has. There we go. Okay, so here's the results. So the machine learning outputs, every word that the machine ran into was given a score. Big positive number means it's a term that makes me think PMI. Big negative score makes me think it's a term that is not PMI. When I'm just grabbing some of the more important PMI and not PMI terms here. So things like residual, 347SS, 5CR, Monel, Hastelloy. Those are all very like PMI flag words. Negative terms, CS or carbon, like carbon steel, tends to make us think not PMI unless there's other things that are changing that. PVC, spiral, gaskets, copper, those kinds of things, less likely to be PMI'd. The machine was able to infer all of that. Again, the machine doesn't understand what any of these words mean at all. It has no idea what metallurgy is. It doesn't understand anything about your facility, but it was able to figure out, hey, this makes sense of the data that I've seen. And once it had that, it was able to go make predictions on the original data and say, okay, if I've got these entries that have these words in them, is PMI required or not? So it'll produce a true false flag of yeah, it needs PMI or it doesn't need PMI, but it'll also produce a confidence score. So again, I mentioned this before, the machine's really good about knowing what it knows. It's also pretty good about knowing what it doesn't know. So in terms of confidence, if I see 99% confidence, the machine is very, very convinced that this is a PMI required entry. 80%, it's also feeling pretty good about this one, but it's not as confident as that 99%. One thing that was fun when we did the review with the customer on this, we sorted the entries in terms of most confident to least confident. We were just looking at the things that were flagged as PMI that they had not flagged as PMI. And as we were going down the list, I mean, they agreed with everything that the machine had said. Like, yeah, that's PMI. It's totally PMI. We missed that one. Yeah. Finally, we get to like 55% confidence. So at this point, it's more or less coin toss. The machine really isn't sure what's going on. It's basically barely erring on the side of PMI. Once we got to about 53% confidence, that's where the humans couldn't tell anymore either. Like nobody could tell what was going on. It's just the language was too ambiguous.
It was hit or miss, that you might pick one that you could figure out, and you might pick one and you couldn't figure it out.
Yeah.
And so,
So overall, I mean, the buy-in from the client was very, very good on this. They seemed to get the value out of this. They agreed with everything that the machine was doing. And in terms of development time, I mean,
so I thought two cool things that came out of this. Number one, the goal was not to let the machine make a decision and then that decision gets implemented. The goal was, how can we focus someone's time to go and review things? So how can I take 500,000 records and cut it down to something that hopefully is a lot less than 500,000 records, so that we can review them and make some decisions on them. Some of them were easy calls. And I think we got to the point where, as our confidence level was higher, people were willing to just go make that change and require a PMI inspection on those components, versus confidence being lower. Man, maybe I do a little bit more review. The time it took was probably the biggest win here. I want to say we gave them initial results. Here's what percentage correct, and this is what it looks like within 30 days of starting, 30, 45 days of starting. Unfathomable with hundreds of thousands of records. And by the way, across 13, 14 refineries. We were also, interesting enough, able to trend some adherence to rules as well through that. But man, getting results that fast on something that was that critical, finding out whether I've got the wrong material installed in some HF alkeys with as much just pressure as there is on those particular units these days, was a massive win.
And of those 30 days, that was the time that it took for the data science team at Pinnacle to develop the solution for this, because we had to do some special things with this just because of the way that the data was structured and the problem that we were trying to solve. That took a little bit of like research and development effort.
It's kind of a bookend though, from the time that we got the exports to the amount of time until we were able to give them preliminary results. Now look, there's been a lot of smoothing over that's happened after that. We did some categorization. We allowed them, we said, hey, here's some prioritization based on what these results were to really enable focus for SMEs. The story here was, how do we use data science to focus expertise, not how do we use data science to replace expertise.
Right.
Yeah, so I think that was critical.
But now if that customer were to say, hey, here's another 500,000 rows, can you tell us what we need to worry about? Then it would take, the computer would take probably 5 minutes. It'd be quick.
I say couple hours. He said
it's about 5
Clearly,
minutes.
I don't know what I'm talking about.
It's probably more than 5 minutes. Not 2 hours. It'd be quick. So here, you had mentioned this. This was kind of another one of those unexpected surprises that we had on this project. What we did here is we're looking at every site in their ecosystem, and we're looking at how often they showed up in the PMI database and how often the classifier disagreed with the things that they were saying. So two that we'll point out here. Green circle, this is a nice happy site. This is one where they're very, very common in the data set. Like it's one of their bigger sites. And they have a very, very low error rate. The classifier loves what they're doing. They can make sense of what they're doing. The one in the red circle, this is where they're not as frequently expressed in the database. Like they're not using the system as much. But the classifier is really struggling with them. Turns out different sites had different rule sets for doing PMI. That was something that we were able to go over with the client. And
interpretations of things, or just adherence to rules.
No,
that was interesting. I agree.
Okay. So that's everything that we were going to talk about.
Let's save some time for questions. Can we process through these pretty quickly?
Oh, yeah. I mean, I think the major things that we wanted to get across today is that we all have a lot of data. We know we have a lot of data. Having humans manage the data is hard, but machines make this a lot easier. I don't think we tried to say, hey, these are the only things that you can do with data science, but it was to kind of inspire, give you ideas of just what can you do with these techniques. And for those of you who are working in these kinds of fields, I mean, I'm sure your ideas are sparking of other things that you can do. Sky's the limit. There's so much that we can do here, and that's a great place for us to be as an industry.
Yeah, that PMI project came out of a lunch that I was having with a reliability owner at that refiner, and it was telling him about some of the ways that we've used data science and machine learning. And he didn't have the idea at lunch. I think it was a day or two later, I got a phone call like, hey, you said that you could do this stuff. What about on this thing over here? So just this kind of inspiration. One of the ideas behind this webinar is kind of show you how machine learning can be used, and hopefully it sparks some ideas for people.
All right.
How about any questions?
Thanks, guys. We had a number of questions come in. I know we're down to the wire on time, so maybe we could just get to one or two, and and then call it. But so first question came in was kind of like balancing, the SME and data science, and where's that sweet spot, and how do you transition from a heavily SME based approach to a more data driven approach? Could y'all speak to that a little bit?
Yeah, I can talk to that. I'm sure you're going to have some thoughts on this too. I know with a lot of the techniques that we develop, they inherently use prior SME knowledge to kind of, in the parlance of machine learning, to regularize my model. There's a whole lot of machine learning models that can explain my data really well, but only some of them actually like have physical significance and would pass an SME smell test. Those are the ones that we want to focus on because they generalize well and they're going to do a better job in the field. So I think with everything that we do, we always have SMEs involved in our review process. Like we will never let data science just kind of run amok and come up with its own solutions. We're always bouncing that off of the people who have had decades of experience working on these kinds of problems to make sure that we're not, going off the rails or doing anything particularly strange, and making sure that that SME input is kind of built into the methodology that we're using. In our minds, is crucial. If you don't do that, again, you're asking for problems down the road. So that's something we take very seriously in our approach to data science.
Yeah, I'll probably bastardize your supervised word from earlier, but this is not a Palantir type approach of dump all the data in the top of a hopper and then walk away and later the computer will bring you some insights, right? I think we come from an industry where expertise is highly regarded, highly sought out, and it's important when you have it. What we're really trying to do with this is use that expertise to build the best automation, if you will, and then use that expertise or use that automation to focus those SMEs' future efforts so that they're able to get to more things than they would have if the machine wasn't helping them.
Got it. Thanks, guys. Well, out of respect for all the attendees' time, I think we're going to go ahead and call it here. But thank you again for taking the time to share your insights with us today. Thank you to Pinnacle, and thanks to everyone for joining us for today's webinar. Hope you enjoyed the presentation. Be on the lookout for a follow-up survey to let us know what you thought about the webinar, as well as any topics you'd like to see covered in the future. And with that, today's webinar has concluded. Thanks for watching and have a great day.
Bye, everybody. Thanks.
Thanks so much.